name is from Georgia, and today I will be presenting from number 12, Gyroscope Teslameter. So first, let's get familiar with the problem statement. If you have a conductive but non-ferromagnetic material in the magnetic field, rotating, it's going to slow down. Yes, it's going to slow down. And my aim was to investigate how the deceleration of this conductive material depended on relevant parameters. So, for the presentation plan, first we'll make an introduction, and to be completed, we will talk about the variable parameters of these phenomena and the experimental setups. Second, we'll see the qualitative analysis of preliminary observation and explanation of the phenomenon. Then we'll talk about the numerical model that I have, the circular model that I have for this problem, and finally we'll make it for the introduction. First we have some variable parameters. First, for the disc, this was with disc materials. So I used three kinds of discs: the aluminum, brass, and copper. And for the dimensions of the disc, I changed the radius of the disc. Variable parameters for the magnets. I changed the magnet shape. I used two types of magnets and negative magnets. I changed the magnet position, and I also changed the magnet strength. Now for the experimental setups. I used several experimental setups for the problem. First one was this copper plate gyroscope, which I had for kind of preliminary observations. And while rotating this bearing, so to say, I changed the position of the magnet. The second experimental setup that I had was this one. So, my discs were these different materials were quite thick. So I tried to use a drill which had a bubble plate to start the rotation of this disc, which was just bearing to this. Yes. And the third experimental setup that I had was for the thinner discs, and when I changed the radius, I used these thinner discs, and I tried to put it on the rotation sensor, and I used to change the position of the magnet with help of this construction. So for the qualitative analysis, for the first preliminary observations, we could see that the distance of the magnet, affected the phenomenon, like how fast this would stop rotating. The next one. And we also tried to investigate the magnetic field, like the fields of the magnets that I used. And for that we used a motion sensor and moving body, at which we had the magnetic field sensor stick, so to say, and we also had this magnet. And as we could see, this magnetic field over the distance graph was decelerating exponentially. So because of it, I made an assumption. That after when we go to the numerical analysis of our theory, we will see that the magnetic field, the main concentration of magnetic field, is magnetic field strength is concentrated in the area just under this magnet. Now, for the explanation of the phenomenon. As you can see, when this disc is rotating and we have a magnetic field that goes through it, for example, we will have Lorentz force affecting and applying force to the free electrons that are in this conductive material. And similar to the Hall effect, this voltage, this charge will be positioned shown in this area, and we will have a current going this way. And because of it, we will have a force of ampere working in this direction. And as you can see, this force is slowing down, opposing the velocity vector. So this force that we get from the magnetic field is slowing this disc down. Now, for the numerical model. As we already mentioned, this force This force is written for like a single part. For the single the force magnetic force applied is like single point at this of the disk. Well, we have like a current density, we have magnetic field strength, and we have this dV, which is the volume of the disk. Well, like the only unknown quantity that we have in this equation is this current density. Now, to calculate this current density, well, if we only had an electric field, well, it's apparent that we only would have this part, which is general Ohm's law, but just because we have the electric field, the magnetic field as well, we add this part, like if this electric field is a force applied to this one charge, it's a unit charge. This part is a magnetic field force applied to the unit charge. Now, so now in this equation, the unknown quantity again that we have to find is this electric field. So how do you find the electric field now? Well, to find the electric field, let's first determine the charge on the plate. Like, the charge cannot be accumulated like infinitely on this plate, right? So we have to determine this limit, like when this charge is going to stop accumulating. Well, this charge is going to stop accumulating when this when the charge already on this like side of the plate creates electric field equal to the magnetic field strength force applied to the other electrons. So, like if this is the already accumulated field, and this is these electrons coming because of the magnetic field applied, and when these two equal to each other, if the charge will stop to accumulate. So this is what we have written here, and with help of from that we find the surface density of the charge. When we find the surface density of the charge, well, we determine the charge, and go to the next slide. And with help of that, we can actually write an electric field at any point created by this and this part, so to say, of this of the charge plates. If we consider this part of the magnet, like this is the front side of the magnet, and under this, and these two are this charge plates, so it's X as a charge plates. So this is how we determine this electric field. Now let's get back to what we're trying to do and find the source. Like if we write now, what this braking would look like. So the braking would look like something like this. Well, do we have like two kind of forces, I think, like trying to stop or slow down this gyroscope? Well, the first one is, M1, that I call is magnetic drag force torque. So magnetic field, from this previous equations that I showed, we integrate this magnetic torque created by this magnetic field, where we have like A is this thickness of this disk that I used, and X, Y, and Y show the parameters of the magnet, so to say. Now go to the next slide. And M2 is this air and other forces that create a torque without like having a magnet that that try to slow down this process of the rotation of the disk. Now, how do you calculate the drag force coefficient alpha 2? Well, if you just write a formula if you just write the formula, if you just write the formula without considering a magnetic field, if you don't have a magnetic field, and just try to see what's happening and how it's slowing down, and we try to get experimentally when the omega angular velocity is going to equal to half of the initial angular velocity of this disk. We can put in all the known quantities and determine what the alpha 2 can be. But, well, this is an assumption, right? We have to check this assumption. To check this assumption, we just get the theoretical and experimental, well, theoretical graph according to this alpha 2, and then we get experimental graph. Well, it takes experimental points, and if they like, if they are in good precision, then we can say this is a good example. But as you can see, unfortunately, as you can see the previous one in the previous graph, the last part was the last one was. The last part was like non-precision. Why did this happen? Because when we have this formula, this t is like can go to infinity. So to have a good comparison, we decided to have a comparison of theta coefficients, theta angle that this disk tried to go through before it stopped. Go to the next slide. Now for the experiment, well first I'll show you the experiment what is changing the position of the magnet. As you can see, we change the position like this. Go to the next slide. And well, this is this distance from the this is the maximal deceleration depends on the distance from the center. As you can see, it was maximum at like 30 millimeters. And we can also see on this chart the distance centimeters, like the theoretical and experimental results. And as you could see, the best one was kind of near the edge of the disk, which is logical because of the moment of inertia. We would have the maximum moment of inertia at the edge of this disk. Now, when I change the magnetic field strength, we could see that, well, all of these are exponents, but because they're like decreasing like after a very long time, because that they look like a linear graph. So this is a theoretical and experimental graph for distortion when changing magnetic field. Sorry. So this is my reference today.
Okay, we're out of time, so let's thank the reporter for the report. And we move on to clarifying questions from the opponent, please.
Okay, could you please say how you measured the area under the magnet?
I just took the...
I assume the area was in your integrals, and how did you measure the area of the magnetic field below the magnet?
Well, I took the, as I said in the beginning of the presentation, I tried to use to assume that this area just under
the magnet.
So I took the parameters of the magnet.
Could we go to slide 21, please?
Yes.
Yeah. Okay. So it seems like the angular velocity stops rapidly at some time. Could you give a brief explanation for this?
Yes, of course. So this is an experiment.
Yeah. Okay. At the end of the experiment.
Yes,
it stops rapidly. Okay. Never mind. Did you somehow try to calculate the current inside the disk? Current.
How did I calculate?
Did you try to calculate do you have a number perhaps, or where?
Well, I didn't have an
How did you calculate the current?
This is how I calculate this. I had one, so I just got that. Yeah, this is the formula. This is the formula of how I calculate the current.
Okay, thanks. Did you try to make a Teslameter out of your disk so that it stays in the name of in the title of the task?
If you mean the what do you mean?
Like to measure the magnetic field with your magnet.
Yes, I did measure.
Did you measure the magnetic field by using your disk?
Oh, no.
Okay, thanks. Can you show, are you able to show us later in the discussion some relationships for the different materials of the disk?
Yes.
Okay, thanks. Okay, brief explanation, why didn't you use a C-shaped magnet?
Yes, out of time. So now we have your preparation time.
Posing this task. Okay, first, let's read this problem statement. A spinning gyroscope made from a conducting but non-paramagnetic material slows down when placed in a magnetic field. Investigate how the deceleration depends on relevant parameters. We saw some tendencies from different parameters that the reporter investigated, but we did not see a clear statement why she opted to use a disk instead of a gyroscope. We'll get to that in the discussion, but we think it's quite an interesting point. We got from the presentation we got a clear statement of the quantitative theory behind the phenomenon, but we like a clearer explanation of how current flows in the disk and how the current flowing through the disk affects the deceleration and the forces acting on the disk itself. She had a thorough theoretical model, which we'll be discussing in the discussion, but we think that this theoretical model could have been overlaid or somehow compared to their measured data, and we would see whether their theoretical prediction was somehow correct with corresponding with their measured data. They had two different graphs on slide 26, where they had their theoretical prediction and their measured data. And I think it's quite trivial to connect these two data sets and compare the theoretical model and their measured data. We find nice that they changed different parameters, such as the distance from the magnet, the disk size, and the disk material. We think that this crucially affect the resistance of the forces acting on the disk by changing the current flowing through the disk. But we did not see a clear output from this changed data parameters. The quantitative explanation, we did not really comprehend with what the reporter was stating. We kind of got lost in the flow of the whole process. We'll get back to that in the discussion. She stated some sort of the drag acting on the disk without the effect of the magnet. We think that this could have been thoroughly measured by simply placing the disk outside of the magnetic field and measuring the deceleration of the disk outside the magnetic field. To the final point, as the name of the task clearly states, it should be a Teslameter gyroscope, which intuitively suggests that we should use the device that we built as a Teslameter, therefore use the deceleration of the disk to measure the magnitude of the magnetic field in which it's placed. We asked some clarifying questions about the shape of the magnet and why she opted to use a non-C-shaped magnet, but we did not get a clear statement of why was it so that a non-C-shaped magnet was used. Now I'd like to get to the discussion.
Okay, thank you, Tony. We move on to discussion.
So the first point that I had was why not measure these like these forces in the gyroscope.
Okay, let's get to the basics. Could we draw the disk, the magnetic field, and the forces acting on the disk, and what are these forces created from?
Can you show this? So we have this disk, right? So this disk is, for example.
Okay. Yeah.
Okay. And this disk is rotating, for example, this angular velocity.
Okay.
Let's, like, for example, see this point, right?
Yes. Okay.
And the velocity vector would be.
Yeah, sure. It has some angular velocity.
Yes. And the velocity vector at this point would be directed to this one.
Yeah, sure.
Okay. Then we have a magnetic field, for example, that is going like, I don't know, certain angle.
Okay, sure.
So, if we have, like, we know that the force,
Okay. Force is quite a step ahead. Let's look at the induced voltage, for example, by this.
You asked me how the...
Okay.
I'm trying to explain.
I think that's a process to get to the force.
Yes, and if you give me time, I can do it. Yes. So, if you look at this, we know that this F force is a multiplication. Cross multiplication of this magnetic field and this vector.
So where the voltage will be purple, be the plus part of it.
We agree that this is the direction of the Lorentz force.
Yeah, right.
So Lorentz force would get this Lorentz force would make this plus charge to stay in like one place.
Yeah, okay. Is it around the whole disk?
It's not around the whole disk.
Okay.
And I already said, when I have a magnet, for example,
Yes.
and I'm like looking at this
Yes,
picture from
okay.
like this upper side, so to say,
I
we say that this magnetic field, like the whole concentration, like the most of the concentration of this magnetic field, goes through just under the area of this magnet.
Okay,
So
okay, I see.
Because of
Okay,
that.
so man, you say that there's some minus here?
Yes.
Okay, so this is the like plus or minus in a loop. Okay? Like electric, the circuit, electrical circuit.
Like, okay, but it's
Yes,
more
okay.
like a charge plate, but,
Yeah, okay, but current flows here. Does it?
well, no, it's not correct. Because, as we can see, this thing, like charge plates, create an electric field, right? Which would be directed like this.
Okay.
Wait.
Okay.
But when we have when inside these charge plates, we have
Okay.
some neutral charges as well, right?
Yes.
And this electric field would make this just neutral, like this inside these charge plates charges to start moving this direction.
The neutral part will start moving outside the disk.
No, outside.
Okay, so the neutral parts of in the disk will start moving. If this is what you're stating, I highly disagree. I think the main factor behind this is the current flowing through the part, creating a eddy current loop,
Okay, I
and the
understand.
force created by the current under the magnet.
So to be clear, we don't agree on that the current density would be the direction of
Sorry. I'm not really asking about the current density. I'm asking about the current.
Current,
Okay, so show me where the
current is
current.
just the current.
Okay. Yeah, okay. Where does the current flow inside the disk?
Current flows just
From where?
From this minus negatively charged plate to the positively charged plate.
Okay, so you say that the current flows this way, yeah?
Yes.
Okay.
And eddy current is just not relevant, I think. To
Oh,
this,
is eddy current not relevant?
But because eddy current makes these these minuses
Okay.
that we have
I-
to charges to move in the circular path. But when we look at this
Okay, I
picture,
highly disagree
it's
with the statement that eddy current is not important, since
I don't mean that eddy
May-
current is not important, but I say that eddy current is not relevant when
Okay,
we talk
I
about the
also
big picture.
I disagree with this, since the force created by the part under the magnet will depend on the induced voltage and the resistance of the part,
Okay.
of the circuit created by the disk. Can we agree? Okay, so we'll have I
If you think
equal
this,
to
if you think,
voltage divided by R.
okay,
Okay?
but I'm
Do you
not
still
sure-
think that the eddy current is not relevant?
Can we first agree on the definition of eddy current? So
Yeah, okay.
eddy current is just induced current, induced current.
Not really. Okay.
Induced current because of this applied magnetic. When we have a Lorentz force,
Okay.
that we induce a current, which is called an eddy current.
Okay.
Do we
It's
agree on
not.
that?
No, it's not really that. It's you have some current flowing through a part, but the current needs to flow back somehow. It's
Well, if you talk about Lenz's law and
no. I'm talking about an eddy current underneath the part. The current needs to flow around the part to get back.
Yes, so
Okay.
it moves in a circular path. Okay.
So the
What
resistance.
does it change in the phenomena? If this electron
Yeah,
is
it changes the
equal
resistance.
or
Thus
this-
the force.
well, I don't use
Determinant force.
Okay, if you go to the theoretical model, if you could go to the theoretical model, I don't try to
Okay.
get
Could
this.
we move to?
Can I answer for your
yeah,
question,
sure.
please? So when we talk about the current density, I'm not trying to calculate this current density using just this simple Ohm's law. I use the general law of Ohm's law, as you can see. Yes. So can you tell me where I have this R? Only resistance that I have is this sigma function, which is this.
But does this account for the
conductivity.
eddy current flowing around the disk?
What? Well, I
The
personally
whole loop of
still don't understand why you think this just
Okay,
the circular parts of
okay.
these electrons is
I think that this is not really a valid opinion. I think that eddy current should be accounted for in this.
Maybe we could move on to the next.
Yeah, we sure could. Could we go to slide 1? I asked this in the questions.
Yes, and I'll explain this.
The angular velocity stops rapidly for some reason. Not really sure
Okay.
why, how.
So I'll explain once for the slide. For on the 21st first slide, I had a comparison, validation of the
Okay.
state that I had.
Okay.
So, well, first, go to the previous one. in your speech you said that I could like easily calculate this coefficient if I just took this out of the magnetic field, and that's just what I did.
The breaking without the part, yeah, the natural breaking of the...
Maybe I didn't say it clearly. So, I took the disk out of this magnetic field, and then I tried to like investigate how other forces decelerate this.
Okay.
And
what did
how
you get
I did
from
that, like how could I do that? I did like an experiment. I tried to like say this omega was half when this omega like
the time
with the half of these.
When time of the omega was half of the omega.
Yes, I tried to find that time.
Okay, I don't think this is really valid. I think that
I mean, I validated it with the experiment that I made.
Oh, no, we did not see any comparison of the theory
Go
and
to the
the
next slide.
measurement.
This is how I validated. Go to the next slide.
Okay.
This is how I validated these.
Okay, the experimental curve.
And now I try to like explain this thing, like what this like.
Yeah, okay.
What this
So
means.
you stated that you measured the natural breaking from some time for this to decelerate to a half of the original deceleration.
Yes, well, like, for example, this is a graph, right? This is an experimental graph.
It's a graph.
And that's like the starting angular velocity.
Yes.
I see when it's like partially like hard, for example, like this point.
Yes.
So I know when it's half, and I see the time when it's like
Yes,
half
okay.
of
What
this
does this
initial
tell you?
angular velocity. Well, I get these terms, like for example, I know this thing, this
Yes.
is I know well an upper number, and I know the t.
Oh,
And
so
then
from
I
this you
calculate
calculated the
that.
age. Oh,
Yeah.
okay, I see.
And
Okay.
that was an assumption,
Okay,
and
okay,
then I tried to validate this assumption.
okay, I see. I think that this was a valid approach to this
Now
problem.
maybe I can explain this thing, like you were interested like what this was, right?
Oh.
Why it was not
Okay,
like-
could we get to the point, why did you use a magnet that was not C-shaped? Like, I suppose the magnet that's not C-shaped has a magnetic field that flows around the magnet as such.
As I saw when I
And by using a C-shaped magnet, you would be able to concentrate the magnetic field, then you would, the assumption of a homogeneous magnetic field inside the magnet would be
Yes,
more
I understand the question.
appropriate
Yeah,
since
I
the magnetic
understand.
field.
But
Go around.
as you can see on the slide, this magnetic field like really decelerated like pretty quickly. So
Okay.
just like if I had this, if this is this,
Yeah,
this
sure.
is a magnet. If I like just put it just a bit
Well,
like
it's
up.
not about the distance from the disk.
It is about
No,
this,
no,
it's
what
about
I'm
this,
talking
because
about,
If I
no.
think if you have like if this magnet is really close
Yeah,
to this, I think there is like
I see where you're heading, but I'm talking about the distance in the x-axis from the disk, not in the height, but to the side. The magnetic field is not homogeneous from side to side. The assumption of such thing, but I think you measured the magnetic field underneath the disk. I think it comes out clearly from presentation that you said it is a homogeneous magnetic field. We disagree with this.
just
This
because
decision
well,
would be more appropriate
well,
approximation.
actually, well, what I did is like for example, like this time when I
Okay, we're out of time. So let's thank the reporter and the opponent for the Now we have time for the summary of the discussion by the opponent.
Okay, so at the beginning we tried to get to the from where did the forces and this appear. I did not really comprehend what the reporter was stating, and I did not get a clear answer to the current flowing underneath the magnet. I'm not really sure that the reporter understands the basic principles of the deceleration of the disk, and I think that the whole assumptions about the magnetic field and measuring and the way how they measure the magnetic field were not correct, since they approximated the magnetic field as being homogeneous, and I don't think that this is really a valid option. Also, they integrate it only underneath the magnet, and I think that the magnetic field spreads also outside from the direct shadow of the magnet. Thank you.
Okay, yes, we're out of time. Thank you. Clarifying from Europe, yes.
Right, so to the reporter, an actual gyroscope has gimbals allowing it to move freely in all axes. Did you actually do measurements on such a device?
well, if you could ask the second question, the additional slides, I can show you the.
Well, let's start with your opponent then. What's your definition of eddy currents and how do you believe these affect the phenomena?
Well, I believe that when eddy currents occur, the overall distance the current needs to flow is greater, thus the resistance is greater, and the
Do
force
you
will be
believe that
small.
these are most important in front and behind the magnet, or as
No, I think that the whole circuit is important to get the resistance from which we get the current.
to the reporter, how was your magnet moved and how was it placed? And what materials were stand used? Mainly?
I used stainless steel.
Do you believe that the ferromagnetic properties of such a material would affect your magnetic field?
Ferromagnetic materials. If I use the ferromagnetic materials, yes.
As you did with your stand, if I understand. Your stand was ferromagnetic, so that would affect it.
No. The string resilience that I had, this disc.
No, the stand for the magnet. That is.
The standard magnet was not ferromagnetic, it was stainless. And to the previous question,
to
you
your
asked
phone.
about,
Yeah.
do you want the answer to that? Yes, so I tried to see, I wanted to investigate the phenomenon while this disc was.
Yeah, I saw your video here. You still have
Yes,
no
if you
allowing
see the
access.
video, I think it was pretty hard and kind of not possible. I don't know. Well, I couldn't explain.
But you have no gimbals in these
phenomenon working with
videos,
this
so I
one.
must move on.
Just
To
go back.
the opponent, and also you later. What material properties do you believe is most relevant to the deceleration of the
Materials properties, resistance.
so the conductivity?
Yeah, definitely.
To the reporter.
Well, you mean the most relevant?
Yeah.
Well, material would be relative, as the opponent said, I agree with that. Also, the thickness of this disc would be relevant.
And then, how did you control that the angular velocity of your disk was constant at the start of your experiments?
Well, I used this thing, for the thickness part,
So
When I
you
took the
haven't
graph,
actually
we
controlled
don't-
that you have the same angular velocity
when
at the start of each
I
experiment?
took the experimental measures, I tried to take these graphs from the same velocity. For example, once
thank
initial
you.
velocity might be 280 and
Did you
second
do any
250,
repetitions of your
and I took
experiments?
just 200.
Yeah, thank you. Did you do any repetition of your experiments?
Yes, I did.
How many?
3 times.
3 times.
And I can show you these.
How did you check that the...
This is I took this graph 3 times and I tried
Okay, we're out of time, so now we have preparation time for the reviewer.
I'm Torbjörn Onsson. I will give you the review of this session for Team Sweden. Let's start with the presentation summary. First, in the theoretical part, we had created and derived a theoretical model. However, we lacked clear basic physics, why did this edges slow down, which we're filling in discussion later. We also didn't talk about eddy currents, and we didn't really talk about the concept of Lorentz forces. Over to the experimental part, we had investigations with disks with different materials, radius, shapes, and different distances of the magnetic field. However, the disk position was fixed and it was not actually on the gyroscope. We had stainless steel in the setup, which is ferromagnetic, and would therefore enhance the magnetic field of the magnet that was used in the experiments. We did not present any data on varying materials and size for the deceleration. To our conclusions, we had measured deceleration and got a good comparison with the theoretical model. However, there was a small deviation towards the end. A huge problem with this was that we actually looked at spinning disks and not an actual gyroscope. We also did not use the spinning disk or the gyroscope that was asked for to actually measure the magnetic field, which is a part of the phenomenon called Teslameter. So moving on to the position, we had a good part of the discussion clarifying basic physics. We brought up that the only area beneath the magnet was considered, and not that the magnetic field as he drew curved, and that would increase the area of the disk that was had a magnetic field going through it. He also pointed out that the phenomenon wasn't used as an actual Teslameter. Over to some cons. He did not point out that the experimental setup did not include an actual gyroscope with its gimbals allowing it to rotate in all axes. He also had too little focus on the experimental setup, and most important about the deceleration in a magnetic field. he also claimed that natural braking was not investigated, even though it actually was. And we believe that these factors are relevant. If we go to the clashes, we first had the opponent asking about the basic physics of the system, and the reporter also stated that the Lorentz forces induces currents leading to a decelerating force. Our opinion is that we agree with the reporter that we do have these Lorentz forces, but it should have been clarified that this neutral region, here we actually have a magnetic field and an electric field opposing each other, and therefore these will remain stationary, these charges. However, we do agree with the opponent that the eddy currents are important, because we do get the eddy currents in front and behind the magnet, as this is where the magnetic field is actually changed the most over time as the disk rotates. And we also think that the Lenz law should have been mentioned more in this discussion. So if we move on to the second clash, we had a question, why does the theory and the experiment deviate in slide 21? Which is a very good question. We didn't actually have a decisive answer from the report here. And we should have used paired fitting to determine the drag coefficient and make an experimental theory fit. And as it's difficult to determine theoretically. If we move on to the third clash, the opponent asked why we didn't use a C-shaped magnet, and the reporter answered that it's not crucial. And we agree with the opponent that he should have used a C-shaped magnet. And then some missing physics is that we didn't actually look at the gyroscopic precession, and the field should have we should have used a magnetic field to see if it had Lorentz forces.
So we're out of time, so let's thank the review. Including remarks from the reporter, please.
The main topics of the discussion, well, first thanks to the opponent and the viewer. And well, the first topic that we discussed in the discussion was, what main topic was about eddy currents. So I once more will clarify this the thing about the eddy current. So this induced current, called the eddy current, makes this charge to move in a circular path. But when this thing, like as I've shown in this picture, if this thing like rotates when it stands, its rotation doesn't make as much, doesn't make as much impact on this disk as this magnet makes. Applies the force to this disk. And I made an experiment actually. So I'll show you the experiment when I try to investigate if the rotation, for example, of this disk or this like locally created magnetic field would have any any part in the experiment. And that's in there we can see like this is the magnetic field sensor, this is the disk, and there's the magnet. And when I rotate this disk and like got this when I rotated the disk and tried to get this analysis, this magnetic field point was the same as the previous. It was the same as this just the magnetic field. So the magnetic field didn't change. We didn't have any kind of difference in the magnetic field. And for the gyroscope precession, like the only thing I think this the reviewer stressed was about the gyroscope precession. And as I already mentioned, I didn't think it was very interesting.
Okay, we're out of time, so let's thank the reporter for Thank you indeed. Questions from the jury, please?
You have elaborated stuff.
Yes?
I'll start with the review. Did you feel that Lorentz force had no bearing on this particular problem?
I do believe that the Lorentz force is important. That's why I asked for it to be more, or explain more deeply and fundamentally how the axes have to be derived.
Is the Lorentz force important?
Yeah, I suppose so, yes.
Lorentz force?
Well, I personally think it's important to these charge movements, let's say, in the Hall effect part, it's important. But for the deceleration, the main force that decelerates is an Amherst force.
The Lorentz force creates the deceleration of this.
They're kind of the same, but the first part of this.
sure they heard the question. Sorry.
Was there a question?
I'll come back, I'd like someone else to ask a question.
Yes, okay. Other questions from the jury?
Well, maybe
What?
last question. To the reviewer and the reporter, like what would be the voltage? The reviewer said the charges remain there, stationary. Would you be able to measure voltage? If so, around which voltage would it be?
Well, that really depends on the parameters of the different material components of the disk and also the strength of the
But
magnetic field, because the important part is
But
that
there's a voltage you can measure there if you go to the two charge
Yes.
positions.
it really depends, because the magnetic field is what the force driving in the opposite direction, and the electric field will be as great as the magnetic field.
Okay,
So this
the
is
reporter, is
rotating?
there, yeah, you pointed out on the disk there would be a charge, positive and negative charges.
Yes.
Would you be able, with a multimeter, to measure a voltage between those positions if you
Oh,
would connect?
Experimentally, I think it wouldn't be possible because this happens in
But
like a very
theoretically, what
small.
would be the magnitude of this voltage?
Um,
Or is there such voltage, or is there none?
well, there is a voltage, and I
Okay.
think theoretically maybe we could get this number. But well, personally, I think
okay.
we considered that we didn't.
I just would like to have an estimation. If you cannot deal in like 10 seconds, I would like to ask the opponent.
I believe no voltage could be measured.
No voltage would be.
Okay, yeah, Elena?
Sorry.
Oh, let me ask. When you meant that the charges are not stationary, the current flows, and this would be meant.
Yes.
Okay.
So for the reviewer, you said the physics was field should not be assumed to be homogeneous.
Yeah,
And
well,
then, and prior to that, you agreed with the opponent that C magnet should have been used. Yes.
those are two different cases. It didn't actually, it wasn't actually well explained at the time. But if you had a homogeneous field going through the entire gyroscope, you would actually be able to have the Lorentz forces creating upwards and downwards currents in the spinning disk, and this would cause, in the same way that the currents caused by the Lorentz force moving outwards and inwards in the case the reporter talked about, would actually also contribute to the deceleration of the disk. This is another case where you could use a homogeneous field of the entire spinning disk.
Not the entire
Yeah.
disk.
Yeah.
If you had a magnet big enough to cover the whole disk, would this slow down?
Sorry.
If you had a uniform field, this big, this big, will the disk slow down?
If the magnetic field comes from the side, if
Yes.
it comes
Not
right
from the
straight
top
up.
of the side, I don't care, it covers the whole disk and it's uniform.
Yeah. If this entire homogeneous field comes
Yes.
from the side of
The
this,
question is,
if
will
the
the
direction
disk,
is that
will
way,
the disk slow down?
it will, if you have, because you have this upward going.
Well, if we had like on the opposite side, we would just.
No, just a big field, you had your disk spinning horizontally in that picture. Imagine a big field,
Yes.
uniform, will the disk slow down?
I don't think so.
The direction here is important of the uniform field.
Okay. Questions from the jury? Well, we don't have further questions apparently, and we're also out of time, so let's thank the jury for the questions and the team for the answers. The grades, starting with the grades for the report, and the grades are as follows. They are 5, 4, 3, 5, and 5. Next, we have the grades for the opposition, which are as follows. They are 5, 7, 6, 5, and 7. And next, we have the grades for the review, which are as follows. They are 6, 7, 6, 6, and 8. Let's thank the jury for And now we can take the score sheet and look at the grades and justify them. With the report, the single lowest grade was 3 from Phil.
I felt that the report didn't address why it slowed down in terms of induced currents in the disc, and the induced current in the disc caused by the Lorentz force. You can then use the Lorentz force to explain why the disc slows down. That was one. Second one, when you were talking over there on the board, you talked about piling up of charges and something about neutral charges moving, neutral particles moving. I lost it about there. And you talked within your equation something about resistance. I think you had conductivity in there. Are they related? Conductivity and resistance?
Well, yeah, because it's like one
That's right. That's right. You said no, we don't need. So essentially, that's why. I think a far simpler approach would have been to talk about the physics rather than throw in first year university mathematics and a confusing issue with lots and lots of stuff that you can do, for sure. But at this level of explaining the simple physics of something, I don't think it really explains why it slowed down or where the energy went.
Okay. We had at the same time 3 grades of 5 and 3 jurors. So anyone volunteer to comment on these 5s?
So, my impression was that you did a great deal of work and experimental work. Unfortunately, we didn't get a chance to see them, almost a majority. So, I was really sympathetic about the amount of work, but then I was decreasing the grade because we didn't. So time management was awful. On the other hand, I kind of like how you were fighting in the discussion, maybe a bit too much, but still it was on positive side. And then the latest was maybe the physics wasn't really explained, and the answers to the jury wasn't positive. So I was super optimistic in the beginning, but then increasing, and to be consistent with the previous one, I did.
Okay. Lars, yes?
Well, just to say, I mean, you had a very nice setup, like your setup. And we didn't get to see exactly like the whole results from this setup, or presented, but in theory, in conversion, in experiments, not in the nicest way you could do. If you predict an experimental decay, show us a comparison of the decay rates, and not just the plots for all different experiments.
Okay.
For instance.
Yeah. My short comment, I had a grade of 5. You had a potential for a very good report with very high grades because you had a great setup, a lot of mathematics, a lot of interesting ideas. But then you had, as other jurors explained, shortcomings in various topics, and therefore, I was first adding points and subtracting points, and at the end, my grade was average, a grade of 5. I still think that you had a very good report, but you had the potential to do it better. I think there was a comment from Eva.
She hasn't proposed how to measure the magnetic field. In this sense, it wasn't the Teslameter.
If I can just comment on that. So, someone, I think opposition was just like, oh, but you didn't use that for measurement of the magnetic. And it's actually not what the problem states. Even though the title is Teslameter.
In the title, yeah.
Yeah, so, but investigate how the deceleration depends on the relevant parameter. So in that sense, I was against your negative comment on that. So I was with that.
Okay. If we look at the grades for the opposition, we had 2 lowest grades of 5. Again, one was from me, one was from Milena. In my opinion, your opposition was good, but again, I had an overall feeling that this was an average level good opposition, and you had the potential to go better, and in particular, there were a lot of aspects in the report that really deserved a lot of feedback and a lot of discussion and a lot of conclusions from your end, saying, okay, reporter said such and such and such things, and we really want to make a conclusion that, and then you say something very objective about the report, give your feedback, because the report from the point of view of contents and structure and physics had a lot of aspects that you needed to correct it. You were doing this well, very well, but I had an impression that you could do it better. At the opposite end of the spectrum, Eva and Lars, they were putting the higher grades for the opposition, the grades of 7. Maybe you could comment on those grades.
The largest is opposition. It was a difficult situation because he tried to ask another question, but she insisted on her opinion and she wanted to explain some not correctly. It was difficult in this situation, in the different situation. We better.
Okay, Lars?
Well, we came after 7 because I ended up like your questions so far. I think it's like the best. Like you clarifying questions, but also very crucial questions, which you get some more time. I think you get very balanced. Not yet 2 points, but I gave you 1.5. Then the opposition speech by itself, well, it could still be better, but 2.5 points. Also, I pretty much liked it. And then you went a bit less with 2 points in the discussion to the report itself, because it was hard for me to give you a grade here. Because on the one hand, you brought up the crucial points, gave it the weight, but in the end you ended up giving it too much weight and not concluding it at a reasonable point of time. But so then you get 2 points in the opposition and yes, no subtraction from the questions.
Okay, yes. I have a general remark that in the discussion, I think the reporter and the opponent had obviously different points of view, but they were not always listening to each other and reacting to each other's questions. And this is something especially that can improve, but difficult to say how, but obviously, yeah, it will be better. As for the review, we had 3 lowest grades of 6, which are already quite high grades, higher than the average level. Perhaps someone with a grade of 6 would like to comment on them? Still probably? No? Okay.
No, just joking. No, I think we did sort of did. I think the notion of eddy currents through your reading thing. You could call that whole current circulation an eddy current. An eddy current exists because of an homogeneous magnetic field. It's not just this mirror thing that appears as little loops in textbooks. It's actually caused by the field distribution, which is what the whole problem is about. So you seem to get a little lost with the eddy current and as if the braking force was something else. But I don't believe that it is. I believe that when I said about the whole field, my intent there was to say, well, if there's no change in flux, there's no reducing in matrix. It's real simple. Newell, lens, Faraday, there's no braking force.
I'd like to talk to you in the grade.
Yeah.
It will be very good. As for the highest grade for the review, this was the grade of 8 from Lars.
I found it a very round presentation as a reviewer role. Like, well, you didn't have an outstanding grade in any of them, but good grades in all of them. Like the questions were good. You respected the weights of giving opinions about the presentation of the presenter, reporter and opponent, and you had focused on the discussion point more when I've seen so far almost, and that should be the reviewer work, right? So that's what you earn your bread with, and then yeah, not miss out points 0 because you didn't. And then we get up at 7.5, but I rounded up because I had your whole impression that I gave you sometimes a bit less than you deserved, so then I rounded up to 8 instead of rounding up to 7.
Okay, so if there are no other questions, then I think we're under time pressure because we need to be right in time for lunch and for Physics Fight 4. So thank you for being with us in the stage 2. Let's now make a coffee break for 10 minutes and please be back in time.